Hello. So an ecologist, Emma, was studying diseased pine trees in southwestern Montana. She took data from N different pine forests. Here's Forest 1, Forest 2, Forest 3, Forest 4, and Forest 5. She took data AIYI, where I is between 1 and N, where AI is the known size of the ith randomly selected forest, and YI is the number of diseased pine trees in that forest. Additionally, the diseased pine trees told Emma that the YIs follow a Poisson AI times theta distribution, and the YIs are independent and identically distributed. But the diseased pine trees were so sick that they weren't able to tell Emma what theta was. Luckily, Emma knew math stat. She figured theta was probably a value between 0 and 1 that represented the probability that a pine tree was sick. But Emma wasn't too sure that was the case, so she just figured she would let theta be greater than or equal to 0. And Emma was interested in estimating theta squared. She found the maximum likelihood estimator, MLE of theta squared, to be T1, which is the sum of the YI squares divided by the sum of the AI squares. In this context, that means this is the number of diseased pine trees divided by the number of trees in the forest and squaring that value. And she found the UMVUE, uniformly minimum variance unbiased estimator, the theta squared to be T2, which is the sum of the YI squared minus the sum of the YIs divided by the sum of the AI squares. But which estimator is better? Emma didn't know which estimator to use, so she decided she would run a simulation to decide which would be better. Her simulation was as follows. And so first, she picked a value n for the number of pine forests, and then she would set her seed to be pi, because why wouldn't you pick pi to be your seed? And then for theta squared values between 0 and 400, she did the following. So she ran 1,000 trials, where each trial consisted of first randomly selecting n integers to represent the AIs, which are right here, and she knew that each forest had between 100 and 500 trees, and so she sampled AIs from between 100 and 500. And then she randomly sampled the YIs from a Poisson AI times theta distribution, which is right here. And then she computed the MLE and UMVUE estimators for theta squared using the formulas she found earlier. And then she decided to compute the mean squared error for each estimator, since she knew that mean squared error is a common technique used to compare estimators. And in this case, to compute the mean squared error, we are going to square all the differences we found here, sum them together, and then divide by the number of trials, which is 1,000. And this follows the mean squared error definition, which is the expected value of our estimator minus theta squared squared. And then after completing that, she computed the mean squared error using the fancy ggplot in R. Right here. And so before running the simulation, she thought about mathematically what would happen, or what she noticed theoretically. And so mathematically, she noticed that if we compare T1 and T2, they're very similar, except T2 subtracts off an extra sum of YI's term. And so we see that more noticeable differences will take place between T1 and T2 when n is small, and this is because when n is large, the sum of the yi squares is going to be ginormous. And so subtracting off the sum of the yi's will essentially be nothing. Additionally, she noticed that t2 is always less than t1. And in terms of mean squared error, she knows that since t2 is a UMVUE, t2 is unbiased, and so since mean squared error can be thought of being the variance of your estimator squared plus the bias of your estimator squared, then since UMVUE is unbiased, the mean squared error is just going to be the variance of the estimator squared. Whereas for the MLE, it's the mean squared error is going to combine both variance and bias in a way. And so after she ran her simulation, she did it for small n and large n because, as we said, n looks like could possibly affect how our estimators behave. And so when n, the number fourths of 3, she got the following mean squared error versus theta squared plot. And she noticed that the MLE and the UMVUE appear to be predicting very similar values for theta squared. However, both estimators are much more accurate when theta squared is small and between 0 and 1, which gives Emma verification that her prediction that theta predicting the probability that a tree is diseased could be correct. And her plot for when n is large for 500 trees is very similar in that the MLE and UMVUE are predicting similar values for theta squared each time. However, theta squared performs better when theta is between 0 and 1. Now, she thought, why would theta squared do worse? Why would our mean squared errors be worse as we increase theta squared? And then her friend Brad told her that Poisson's distributions don't really play well when the parameter becomes large. And so maybe it has something to do with the Poisson distribution on why mean squared error is so large as theta squared increases. But overall, since both estimators predict similar values, she figured it really doesn't matter too much which estimator to pick to be the better one. But she ultimately decided to go with the maximum likelihood estimator because it is slightly easier to compute. And so now theta squared was well estimated and everybody lived happily ever after. Well, except the diseased pine trees. They died.